Okay, I think we can start. Thanks everybody for joining this afternoon session. So we are going to have a talk slash discussion led by Arnaud Delfante, who is coming from University of Illinois, Urbana-Champaign. He's going to share some thoughts on asymptotic renormalization. So again, the spirit is that it's 30 plus 30 minutes. You're very welcome to ask questions during Arnaud. He's also willing to trigger some discussion, so please don't hesitate to interrupt. Take it away.
Yeah, thanks. And thanks to the organizers for giving me the opportunity to present my research. And so today I will talk about, I will discuss some notion of asymptotic renormalizations. That is a work in progress with Andrea, Dario, and Carlo. And yeah, let's see, because, I will motivate first my talk. Yeah, so, we all know that, yeah, we can probe the ADS CFT correspondence for lambda for a negative value of the cosmological constant. And in this case, we have the advantage of the underlying microscopic model, which is the type 2B string theory. And there is also the link since the seminal paper of Brown and Eno in 86 about the fact that you can relate the ADS asymptotic symmetries with the CFT global symmetries at the boundary. And in such computation, you can have that, the asymptotic symmetries first, they are distinguished from pure gauge transformation by the fact that you can associate a non-vanishing codimension to charges via the second Nuttall theorem, and then it will give you charge diffeomorphism that will map in equivalent physical configurations. But in such a computation, you can have the possibility of having radial divergences in the computation. Well, you can understand that with the fact that you are going to look at conformal infinity, and in such a case, your field will depend on the radial coordinate. Yeah, the field will depend on the radial coordinate, and since you are going to look at infinity, you can understand that you can have some divergences associated to such a limit. And okay. And then in the ADS case, there is a concrete way to renormalize such computation. That is the holographic renormalization by Skanderis, etc., and collaborators that tells you that you can renormalize in the same way the ADS on the bulk and the CFT on the boundary via the same type of manipulations. And then if you want to investigate the holographic principle for lambda equals 0, so for asymptotic flat spacetimes, you don't have access to, for the moment, to an underlying microscopic model. And so a guide principle for determining some features of such a safety, as you well know, is the asymptotic symmetry ray. And one possible way to look at such a thing, since we don't know what is the boundary CFT in this case, is to try to induce features directly from the ADS via a flat limit. And so that's the way that I will present this talk/discussion, in the sense that I will try to first review what is the ADS holographic renormalization in a simple example of Maxwell, which is the simplest gauge theory, and then see how we can understand the features of such an holographic renormalization in the flat case by taking the manipulations that we have done in the ADS case. Okay, so let's first review the ADS case that is well known. And the ID, for example, I'm looking ADS in D equals 6, just because it will be in the Maxwell case the first example where you have a non-trivial divergences. And then you can take the Poincaré patch. And then you can take the Poincaré patch of ADS, which is this expression where you have the XA that are the boundary coordinates and Z the radial coordinates, such that the conformal boundary is at Z going to 0. And then you can take your Maxwell theory and study the Maxwell equations and do the asymptotic expansion along the radial coordinate, as we well known, for example, in the Pfefferman gram of gravity. And you will obtain this type of expression, where you have that the leading order is completely free. And in the holographic dictionary, it will be the source of your dual CFT. And then you have this subleading order that is completely determined locally in terms of the source. And finally, you have this third order that is constrained by this type of equation, and that will serve, that will play the role of the wave in the dual theory. And then after that, if you want to look at your bulk action and also determine the charges, etc., so you start with your bulk action that I take for this expression, which is not the usual one, but I will explain in the future why I take this type of expression for the Maxwell theory. And well, so I take this form of the Maxwell Lagrangian, and then I go on shell and I look, okay, what are in the asymptotic radial expression of such an expression, what can I obtain? And of course, here I will have the finite value. So the usual one in terms of VEV multiplied by delta of the source. But still at the leading order, you have a radial divergences that takes this expression. And yeah, you want to be able to add a counter term that will be able, when you are looking on shell, to cancel such a divergence. And a way to do it is to look at the way that it is prescribed in the ADS holographic normalization. So by inverting, since here you have the fields that are on shell, a way is to invert your asymptotic field expansion in terms of the off-shell bulk fields, so that you preserve the bulk locality of your theory. And here it is pretty simple, since all the radial divergences that you are going to have in the ADS case are purely locally determined by the source. So it is, nearly for free that you can obtain the locality in this case. And then you have also, so you obtain this expression by inverting the asymptotic expression. And then you have also to look at, to preserve your boundary covariance. So the covariance with respect to the regulated surfaces. And here for example, here I was looking for z equal constant surfaces. So my regulator is z equal epsilon if you want. And I'm going to the infinity like that. And you can covariantize via the induced metric on each hypersurface that you are going to use to go to infinity. So that's the, sorry? D equals 6. Yeah, because D equals 6, yeah, if I went to D equal 4, you just have the leading order, well, the finite order, and you don't have a divergence. So I want to show an example where you have a non-trivial divergence. And so D equals 6 is the first case. Yeah. Yeah, exactly. You could also go to D equal 5, and then it will not be linear, but in the logarithmic way. Okay. And yeah, don't impose any boundary conditions, in fact, because in the ADS case, the fact that you start, yeah, in the ADS case, in fact, you don't have to input any boundary condition, because you can just look at the equation of motion and try to solve it. And if you put boundary conditions that are, I will say, softer than this one, then you have to consider an infinite number of degrees of freedom above the leading order. And so it will explode directly from the solution space. Then in the ADS case, if you don't want such a case, you are forced to start at this one.
Okay.
And we will see that in the flat case, it's not maybe so easy to understand such a manipulation, but in the ADS case, it's straightforward for this one. Okay, and yeah, so that's the picture of the ADS holographic renormalization and for the bulk action. And also then if you want to obtain what is your asymptotic charges, well, of course, you can take just what is the finite term that we'll obtain here via the renormalization. So we'll add the counter term to the bulk action. You will obtain your finite value, and then after that, you can do the second Nuttall theorem, etc., etc. But you could also want to, okay. Yeah, but you could also want to understand them directly from the symplectic structure. And we are going to see that, okay, for the ADS case, it's maybe not super important, but in the flat case, we'll see that there is some distinctions between the fact that you want just to renormalize the bulk action at the boundary, or you want to renormalize your presymplectic structure. And the main idea of this type of manipulation to renormalize the presymplectic potential, so that is determined as the boundary term in the variation of the action, is to play with the higher world ambiguities. And the first one is a boundary term that you can always add to your rational principle that will not modify your equation of motion, but still it modifies the presymplectic structure in this way, but it will not have an impact at the level of the charge, where here it is the symplectic potential that you can, after that you are looking, that you are going to evaluate along a gauge parameter, you can obtain the codemotion to a surface charge. So this first boundary term that we have, that we need to renormalize the bulk action, doesn't play a role in the renormalization of the charge, but the one that is going to play a role is the corner term. So you can always add to your boundary, to your presymplectic potential, a boundary term, since you can understand that if you look now at this type of expression, of course, if you take C mu nu that is anti-symmetric, this type of term will vanish, so you can always add such a term. But this one, in addition to modify the symplectic structure, modifies also the charge. And so it is this one that we will need to take into consideration to be able to renormalize the asymptotic charges. And there has been some prescription to tell you what is the good corner term that you have to consider. And the first one is the one by compare and Marov that tells you that, okay, for the boundary term, you take the one that we have determined for the bulk action, so just the boundary contour term. And then the corner term that you are going to add is the presymplectic potential associated to this boundary contour term. And it will renormalize your presymplectic structure directly. Another way to prescribe your ambiguities is to say, okay, maybe I don't want to consider any boundary action, since at the end, if I want to renormalize the charges, what I need is just a corner term. And so you can try to manipulate this type of expression to replace, in fact, all the, I will say, meaningful divergences only in the corner term. And that's the way prescribed by Laurent, Florian, Aldo, as well as Céline and Robert. And the way is to express then, yeah, you take still that the boundary contour term is something that you don't, yes?
Oh. No, forget this. So do you want to also make sure that this procedure gives you a renormalized theta, which is independent of your choice of regulator, for instance?
Exactly.
This is not automatic, right?
Yeah,
so it's something you need to impose on top, right?
Exactly, I will talk about that. And yes, indeed. So in this case, I do not focus on the BZ, which is the boundary term, but then the corner contour term is prescribed at this way. And it will renormalize your theory up to a boundary term that you have after that to decide if you want to consider it or not. And yeah, exactly. In fact, the LCT as well as the theta ACT, they have also to.
Yeah,
maybe I will answer the first question. You will allow me.
First he answers me, then you can ask.
Yeah. Yeah, so of course, the LCT and the theta ACT, you have to also implement the rules of the holographic renormalization, so that are that they are expressed all shell to preserve the bulk locality, but also that they are covariant with respect to boundary diffeomorphism. And indeed, it's not a trivial way, but in the ADS case, it seems that it is doable, I will say. And in the flat case, I will show that there is some distinction between boundary term and corner term. And I will show that some rules that you can apply to the boundary term, you cannot apply them to the corner term directly.
One of the rules is that theta n should be independent of your regulator. Is that one of the rules?
Theta n, yeah, we said theta n is.
Because manifestly dependent. How you subtract the derivatives.
Yes.
So then you will have to you accept this rule that it should be independent of that, so you should have a method to make sure that it is independent of. For instance, if your renormalization is a cutoff,
Yeah.
well, this cutoff could be a time-like boundary, could be a deformed boundary. You would like this data rank to be independent of all such choices. And you will need some technique to make sure that it is.
But Terrain is the finite expression. It's just the fact that you remove all the divergences. And in fact, here with this type of manipulation, even with this one, you can cancel the leading divergences, but also the ones that are below the finite order. So you just have a finite value of your presymplectic potential.
For instance, what is the parameter that is making these divergences up? Large radius, for instance?
Yeah, exactly.
This large radius is defining a certain foliation.
Yes. Exactly.
I change the foliation.
Yes.
Your divergences will be different.
Yes.
So, right. So you would like that your final result is independent of the choice. That's what I meant. To me, it's not manifest just because you're removing the divergence. It's like in QFT. I mean, you put dimensional regularization, whatever you want to get rid of divergences, but at the end of the day, you want to make sure that your procedure is independent of the regulator, right? So it should be one of the rules.
Yeah, but one of the rules is that you don't have the presence of the regulator at the end. If you choose the regulator R equal constant, at the end you don't have.
This removal is independent of the choice of regulator.
I know, okay. Yes, you can have also that the fact that it is boundary covariant, so it will, if you are covariant with respect to the induced metric on the surface, then you can choose any surface that you want.
Okay, maybe we can discuss, but I would argue that is sufficient only insofar as your boundary diffeomorphisms are allowing you to make you change these choices.
Yeah.
If they're not large enough that they're allowed to do these things, then you might not. Anyway, maybe
it seems that in the ADS case, it's always like that, but in the flat case, I will show that, yeah, indeed, your discussion is interesting for the flat case. Okay. Oh, yeah, sorry.
So this corner term is codimension 2 term or codimension 1 term. So is this same as counter term, or I will just understand it's corner terms?
Sorry, I didn't.
So this LCT.
Yes.
So I will understand is a corner terms or counter terms. So is this codimension 1 term or codimension 2 term?
Oh no, this one.
Codimension 1 term.
Yeah, for example, in this case, it is
so
this term.
Then it's just a boundary term, right? So
it is this term, but well, it depends on your theory. So I don't know.
So
this is the one that will renormalize your theory at the boundary.
On the boundary. So this
Yeah,
LCT is codimension 1 term.
Yeah, exactly.
Okay.
Yes.
So it is not boundary. So it is a boundary term.
Yeah, exactly. And then this one is the corner term. So the one on the codimension 2 surface.
No. Which is
But this one is on the boundary, and this one on the corner.
Yes.
LCT is the boundary, but theta CT is the corner.
Yes.
Yeah.
Yeah, I understand.
Okay, sorry. Okay. Okay, fine. And then, okay, so that's the picture of how we renormalize ADS at the boundary and at the corner. And then I will show what is the idea behind the fact that you want to describe also Minkowski. And just a word about, also all this thing about ADS. You could also choose, instead of the Poincaré patch, you could also choose, for example, the boundary coordinates for ADS, and then deduce what are your boundary terms, boundary contour term, and corner contour term, etc., and make the flat limit, etc., via L going to infinity, etc., etc. But we are going, so that's the way that they do, that they did the normalization in the lambda BMS case, for example. But in this case, I want really to deduce the boundary terms directly from the flat description of spacetime, and to see what are the differences between the two approaches. Okay, so let's move to the flat case. And in the flat case, I will again look at, well, Minkowski, no, but in D = 6 for the same reason for the linear divergence in the Maxwell theory. And so I choose the boundary patch of coordinates, where now U is the retarded temporal coordinate, R is the radial coordinate, so that future non-infinity is located at R going to infinity, and XR are the coordinates on the celestial sphere of dimension 4 in this case. And then you can also look at what is your asymptotic solution space for this type of theory. And if you look at the radial gauge, which is a sort of boundary gauge for Maxwell, you can obtain this expression for your solution space, where you have that the term in blue plays the role of the electromagnetic shear, as you can see here in the electromagnetic flux that is going to future non-infinity, where you have the presence of the news square, as we well known, for example, in the Bondi asymptotic flat case. And then here you have the equivalent of the Bondi mass aspect, which is here the charge aspect determined by the shear, non-locally by the shear. And here you have also, you can have the presence of an infinite number of Chtonian degrees of freedom. So Chtonian means that you are above radiation. And these are determined again by a corner data plus something non-local on the shear. And then with that, you want to also look at your bulk variational principle and to see if you have linear divergences, etc., etc. And in this case, it will not be easy because, in fact, it will, as we can see in this expression of the solution space, here you have the shear at the sub-leading order, but the leading order is something completely independent of the shear. And in fact, this leading order is a pure gauge it takes the form of a pure gauge transformation, because if you look at what is your residual symmetries in the radial gauge, you just have the equivalent, the analog super translation for Maxwell case, so an infinite abelian symmetry. And you have that this phi transform like this in terms of this residual gauge parameter. And so you have this very elegant way to describe your solution space in the sense that you have here the presence of pure gauges freedom. Then after that, you have the radiation and all the radiative things and also the Coulombic, etc., etc. So you have a splitting of your solution space, the pure gauge data plus then the radiative data. And the fact that this, it will play a role in the way that you are going to normalize the action, because if you just look at the on-shell expression of your bulk, the on-shell value of your bulk action, in fact, it will look something like L is going to be something like R squared multiplied by di phi delta Ci plus the finite order. And in this case, well, if you want to obtain something that is bulk local, it's not easy to see how you can invert the asymptotic expression as we have done in the ADS case, because, well, the phi and the Ci are completely independent. And so it has led to some confusion in the literature, where in the first instances, they just renormalized the symplectic structure via boundary and corner term that were completely on-shell, but then it is completely non-local, and then you have to deduce if there is the possibility to have such a local boundary term that is completely non-trivial. And in this case, a way to do it, and that we have done in our work, is to take advantage of the splitting of the solution space between pure gauge data plus, after that, the radiative ones. And by rewriting in a good way the divergent boundary part of your action in such an expression by using some things that are similar to the second Noether theorem, and where here B lambda is exactly the boundary term that you will obtain if you look at your action evaluated along a gauge parameter. So you take really advantage of the fact that you have a pure gauge form expression here. You are able to deduce in a good way what is your boundary counter term in a local way, thanks to this type of manipulation. And it has the good, well, why is it possible in this case? Mostly because here your residual gauge symmetries are completely homogeneous in the radial coordinate. And I will show later that if you look then to, for example, linearized gravity, then you have well, you have the presence of the super translation, but you could also have superrotations. And in the case of superrotation, you don't have this homogeneous transformation of under the residual gauge symmetry. And then we are going to see that it's not possible to place such a trick for super rotation. But for super translation, it's you can always do it. And here we did it for d equals 6 and for spin 1. But well, you can also generalize, in fact, to any value of the dimension of the background and any value of the spin in the linear theory. And to show you these things, well, I can consider this type of higher spin action, which is the Maxwell-like form of the Franzdal action. And I can impose these Bondi-like gauge conditions that are inspired by the non-linearized gravity and that are, well, those are on-shell gauge fixings, but there is the same number of conditions that in the TT gauge. And so you impose these conditions, you look at your spin action, etc. You will do all the same thing about the asymptotic solution space, and you are going to, again, have this type of splitting between the pure gauge transformation that are here the equivalent of the super translation for higher spin, which takes this type of expression where we have all the typical numerical factor and factorial factor of higher spin and IRD. And then after that, you have all the radiative data. And you can play the same role with this type of expression to express the divergent boundary part of the bulk action. And then you are able to deduce what is your boundary control term in a pure local way. And then after that, of course, you can look at what is your renormalized symplectic structure or normalized action. And here you will recover the analog of the H-Strecker trouble for higher spin in the linearized theory. And also look at what are your renormalized charges in just a case, which are given by this expression, which is the generalization of the super translation charges for higher spin. Okay, and then after that, you can also say, okay, you have renormalized your action, etc., at the boundary, but what is going on the corner? And then we will see that it's not the same way that we can do it for the boundary term. In fact, if you look at the corner ambiguity, it will take in this expression, well, it is prescribed, in fact, by our method to renormalize the boundary action to be equal to the divergent terms that are present in your charges due to the splitting of the pure gauge transformation plus boundary data. And so it takes this type of expression. And now, in addition to the type of term that you have the phi multiplied by the shear, you have also the presence of Octonian degrees of freedom. And then, well, at least for the moment, we don't see a way to be able to deduce a local corner control term that will be able to renormalize this thing on shell. And well, one of the main reasons is that, well, you are stuck with this type of expression. Well, for the shear and the pure gauge data, we know to do it thanks to our method. But for the Octonian, we don't have a way to see how is it possible. And okay, what are the tentative solutions that we can try? Well, there was a proposal by the team of Capone et al., where they tried to impose corner condition on your field. So by, for example, saying that your shear in the spin 1 case will be equal to 0 when you will look at future infinity for you going to minus infinity. But then in our case, still you are maybe able to normalize some terms due to the presence of the shear. But then after that, for example, for spin 1, for d bigger than 10, you then have the presence of non-trivial contribution of the Octonian that you are then not able to cancel via such a corner condition. There is also the possibility to start from a static system. So then you are going to say that for such, you below U0, you don't have radiation, and then it will mean that, and you also assume that your field attains a stationary solution, then you are able to cancel all the presence of radiative data, so the shear, the Newtonian, etc. And then, for example, the AU will only take the expression starting from the Coulombic order with the pure Bondi mass-like aspect, which is the corner data that depends just on the coordinates on the celestial sphere. And then you don't have any divergence. But maybe, yeah, it seems to maybe be maybe too strong condition on your fields. And in principle, you want to impose, yeah, you don't want to impose anything on your field. You just want to consider this corner of shell term on shell term and see if there is a way to deduce an off shell term associated to it. One other possibility, due to the presence of Newtonian, is to maybe try to understand what are really Newtonians. Are there new degrees of freedom, or are they reminiscent of the fact that here we consider future non-infinity, and maybe there is some reminiscent radiation coming from past non-infinity, etc., and that there could be associated to that. And so maybe with some type of conditions adapted to such a case, maybe you are able to normalize not only the shear, but also the Newtonian. Okay, so that's the picture for the corner term where we see that it's not that easy for the boundary term. And then I will also show that for the superrotations, it will be even worse than these cases. In the sense that, yeah, if we look at spin 2, so the First-Pauli action, in D equal 4, we have this type of solution space where you recover the shear, the news, the mass aspect, etc. And you have also the splitting with here the pure gauge term, where you have here the super translation part of linearized gravity, and here the superrotations. And then you can look at your boundary and corner ambiguities that you have to consider. And in D equal 4, it's fine because the boundary term, you don't have to renormalize it. But for D equal 6, we'll need to renormalize it. And you cannot apply the same rule that we have done for only support translation due to the presence of the fact that your gauge transformation are not homogeneous under radial coordinate, on the radial coordinate. Yeah, so this one, so it was this type of manipulation to rewrite the divergent boundary part of the actions. And it plays on the road that you are able to make a distinction between the pure gauge data and the radiative data. And it was, well, we were able to manage to rewrite in an off-shell way, thanks to the fact that it was only homogeneous in the radial coordinate. Because the expression then it was completely easy since you have just delta of AI, delta lambda of AI is just one term. And then you can see that it is easy to see, okay, how we can invert the expansion. But if you have two terms, you are again stuck with such an expression that you don't know how to invert in a local way. Okay, so for superrotations, we are not able to do it anymore. And here in D equal 4, it's fine. But for D equal 6, you will need to renormalize it in such a way, but it's not possible for the moment. And we also see that directly from D equal 4 for the corner term, we again see the presence of such a term that we are not able to renormalize in a local way. Again, due to the presence of the shear and some independent data due to the superrotation. And then you can ask maybe, yeah, because this expression is typically the one that is set to 0 by the conformal killing equation of Barney-Strosa. And then you can say maybe, yeah, I don't know, maybe the superrotation, you could say, okay, I want to consider Barney-Strosa. And then you are able to normalize D equal 4. But in D bigger than 4, this type of expression, on condition that you are going to impose on your vector on the celestial sphere, it does not give you an infinite family of gauge parameters for D bigger than 4. So you don't have this enhancement of superrotations. But if you consider this type of complicated rotation, superrotation, then you are stuck with this term, but you are able to go beyond d equal 4 and to have also the superrotation for d big under 4. Okay. No question? Okay. So I will move to some discussions. Yes?
The paper by that you referred to in the previous slide. Yeah,
This one?
this one, that they renormalize the charges of the superrotation in 6D and higher.
Only at the corner. And indeed, they did it at the corner by imposing such condition. And also in our cases for d equals 6, at the corner and at the boundary, of course, we are also able to renormalize this thing, thanks to the fact that you are going to set Cij to 0 for you going to minus infinity. But if you don't impose this type of things, you don't know. And in their paper, they don't discuss, for example, the boundary term, just the corner contour term.
Thank you.
Maybe on the same slide, could you comment maybe these three tentative solution, I guess they want to achieve specific, they have in mind specific properties that they want to achieve. Could you comment on which solution is a good one for which cases?
I don't remember. I think there is some geometric way to impose this thing, but I don't remember exactly. So it's not that sharp. They don't say, okay, we just input this condition on the shear. They have some reasons because they look at some geometric way to describe the solution space, but I don't remember exactly.
And so it means the other two have different desirable features. Could you maybe explain?
Well, this one is just that, well, you want to start from you can say that you start from a stress energy solution and then you will make evolve in the time to see what is going on. So that's a way to renormalize. I don't know what they were thinking in deep, but well, at least it's a way to remove the divergences. I don't know what can I say more. And for the last one, well, it was just that they want to understand what is the meaning of this Tonian to see, because if you don't, well, for the moment, the current understanding is that you have an infinite number of degrees of freedom, but you don't know, there is some thing that you can do with that, but are they physical or not? Are they reminiscent? Are there new things above of the others? It's not clear for the moment. So they want to understand if it is related to some radiation, etc., etc. Okay. So a short summary of what we have seen is that, if you want to explore aspects of flat holography, the asymptotic symmetry way to do it, you have, in most cases, to renormalize the theory to, in fact, give physical meaning of what you are going to do with this thing. And the results that we have seen is that we have now a method to deduce a local boundary control term for any spin and any d for support translation. But then there is still some work to do for corner control term and superrotation. And so to understand what is the real meaning of the corner control term, do we really need them? And maybe also to discuss maybe the physicality of the superrotation for IRD and this type of things. And future possibilities and future discussion that I would like to address is that, well, first there was also notably by Luca and also by Robley, etc., they discuss how we can deduce the maximal number of what is the maximum charge algebra that that a corner can support. And then you can say, okay, in their analysis, they didn't discuss the renormalization, etc., but they obtained that a corner can support this maximal number of charges. But then what is the link between their analysis and the fact that we are able or not to renormalize? As we have seen here, it's not completely straightforward. You can normalize the flat analysis. And so what is the meaning that we can address to this asymptotic corner group? And maybe a way to see it is maybe to look at the quadrant orbit methods and to see if, well, the boundary and corner contour term are associated or not with some orbits in this analysis. A way also that maybe we can improve all the stuff is to try to understand how we can, well, if it is useful or not, to carry on covariantize all the boundary and corner terms that we have via the null hypersurface geometry. And yeah, finally, also a thing that I think will be important in the future is to describe the well, flat is fine, but maybe cosmology is even cooler. And for example, if you want to describe asymptotic FLRW spacetime, you can via a certain model of universe obtain BMS-like transformation at a future null infinity, and then you can say, okay, maybe I can implement the techniques of flat renormalization through the FLRW case to give also a sense to such manipulation. And also in the FLRW spacetime, it seems that maybe you are also able to make a splitting between residual, pure gauge transformation plus then the radiative data. So all these methods that we have done to rewrite the boundary different part of the bulk action could be also applied in such an analysis. And voila, thank you very much.
Thank you, Arnaud. Are there more questions, comments? Simon?
Yeah, thanks. Yeah, my question is, you focused a lot on even D. Of course, we know that odd dimension is a bit special for many reasons, but with regard to holographic normalization, is it better or worse to what's happening in odd, even D?
I think that the way that I show to normalize, at least for super translation, I think for even or odd D, it will work in the same way. Maybe what you can have is to add log terms, and maybe you are going to have some log terms that you cannot rewrite in a local way as you have in the ADS analysis, where you have the presence of some anomaly associated to them. But in principle, in the odd case, what you are going to have, well, also in the even case, you can add logarithmic terms, etc., and discuss them. In odd D, you are not, well, it's not necessary, but yeah, it will not modify all these things. A priori here, it works for any D. It's just that, yeah, here I showed D equals 6. If you look at D equal 7, what you're going to have is not integer, but half integer, etc., etc. But if you don't look at log terms, a priori, it will not modify the way to normalize it.
Okay, so the fact that I have half integer powers of R is not an issue.
No.
Okay.
So here, this your solution space is part of Maxwell equation. So, so my question is, how do you got this follow-off for AI and AU? So
I prescribe the follow-ups.
Yes.
Yeah, okay. So
solving the Maxwell equations.
Yeah, so a way to prescribe the follow-ups. When DSDS case, it was straightforward due to the equation, as I said, because otherwise you are going to have an infinite number of terms above the leading order. But in this case, indeed, you have to prescribe them in such a way that, for example, this flux will not have divergences, because this one is an exact quantity and you cannot normalize it via some higher order ambiguities. So you have to choose your boundary condition in a way that the exact quantities don't diverge at infinity. So that's a way to impose them.
Okay. And at some point you said that this phi is a gauge, right? The phi in the AI.
Yes. This one?
Yeah. So, and this solution is for anti-de Sitter or flat?
It's for flat, this one.
For flat. And at some point you say that phi is pure gauge?
Yeah, pure gauge in the sense that it takes the form of a pure gauge transformation. because AI, well, AI, if you look in the radial gauge, so AR is equal to 0, then what you have is that the gauge parameter is, of course, radial independent. And then what is your gauge transformation? Then you have delta lambda of AI, well, it is just di lambda. And you see that this one transforms exactly as a gauge transformation. And it is the only one that transforms, and the residual gauge symmetry in this case.
Okay, and I have one more question actually. So can you go to this Hij expression for the answers for gravitational case? I think maybe around 10, slide 10 or sometimes. Yeah, this one.
Yeah.
So for this answers also, it is for flat case, right?
Yeah, exactly.
And you got it from the Bondi-Sachs answers.
Sorry?
Because I mean, so this solution, I assume that the data, if you give data Hij, you will get the Hui and Huu from the Einstein equation itself, right? So your initial data should be Hij, and you will get this.
Yeah, exactly, yes.
Okay, so and again, this order R square terms are pure gauge, right?
Yeah, exactly. This one is pure gauge, and also this one because they are deduced from this one. Yeah, you have the Einstein equations.
Okay, and I mean, in anti-de also, I mean, this can involve in terms of pure field, but there are two gauges like psi and phi, and but in electromagnetic case there is one gauge. I mean, do you comment on that? Because I mean, in anti-stellar case, at least you can put off one of these gauges, psi or phi, to be 0, not simultaneously both.
Yeah, exactly.
I mean,
it depends on boundary condition, of course, and that's what I showed before. For example, here with these things here for higher spin, here it is for any s. So if you put s equal to, in fact, you are going to reduce your boundary condition, so you will kill these terms and this term. So we'll start here at the shear for d equal 4. And so it is the case of this pure support translation. And then you can see that if you improve your boundary condition, you are able to deduce a new residual cage symmetry, which are the superrotation.
Okay, thanks.
Maybe one question on the electromagnetic part and one on the linearized gravity.
Yeah.
So the electromagnetic, of course, I'm curious to know more about what the tectonic degrees of freedom are. In the sense, your system is still second-order differential equations, so we still have that the initial data are transverse independent degrees of freedom and Gauss law constrained the dependent degrees of freedom, right? And that's all. So these Tectonians are part of those, or that's what I mean, we know what are the total degrees of freedom, right?
Yeah, but
so
yeah.
Why is it mysterious?
No, I will say, in my opinion, they are not independent, but I don't know how to relate them to something for the moment. That's the fact that here, if you look at the Tectonian, here you have a priori this term that is completely free on the celestial sphere. And what is this expression? I don't know for the moment. And that's what
suppose that you solve the theory using a space-like hypersurface, Cauchy slice, right? Then in that case, now how many degrees of freedom you have? Because in higher dimensions, I have no intuition. I never worked on it, but maybe you know how many you have in that case. Okay. And for the linearized gravity case, then I have maybe a way to, coming back to my previous question.
Yeah.
So one way to make sure that your renormalization procedure is not breaking general covariance would be that once you have regularized, you can compute fluxes, for instance.
Yes.
And then you can look at the Poisson bracket between the fluxes, and that's going to be exact. But if you choose that your initial and final cross sections are, let's say, non-radiative, then it must give you a realization of the BMS algebra or superrotation algebra. So you must get the flux for the Lie bracket of the two generators you have chosen. If you get anything else, that's a smoking gun that the renormalization was done in a way that is depending on your choice of regulator. So that could be an interesting check.
Okay, thanks.
Final chance. Maybe in your outlook, there was a sentence about explore aspects of flat holography. So could you just tell us what, in your opinion, are the main lessons to be learned from this? And
Yeah, we said that we have to see if we can renormalize or not the theory, because it seems that in some cases it's not completely straightforward, and maybe we are doing a lot of stuff. Maybe we have to look if it is physical or not. And so we say we have to insist on what is the flat holographic renormalization to be sure how are things going. And it's not easy because, for example, here I did not describe what is the source of the wave of the dual theory, etc., because, well, for the moment, we don't know for flat holography. And then that's also something where the Carolean covariant ties, etc., could be useful. For example, by using the covariant Newman-Anti, also by following the papers of this guy, also of Luca in January, to see can we deduce something like in the renormalized action of gravity, what is VF multiplied by delta of the source, to see, okay, now that we have the divergences, are the term local or not in the term of the sources or not? And then what can we say about the renormalization? Because if in the ADS case it is like that, what can we expect from the flat case? We try to take inspiration from the ADS case, but maybe the flat case does not work like that. But then what is the CFT, etc., etc.? It's not clear at all what we can do with these things. So we have to better understand these aspects of flat holography to, I will say, to go beyond that.
okay, I think we can give Arnaud a last round of applause. And thank you.